So, hi, welcome to another class. Quick thing is my camera isn't working correctly. Um, so that's why there's two of me at the moment. I can't get the camera on my normal computer to show up anything. So I'm using two computers at once, which is kind of weird. So I probably won't be facing you as much of the class, but I was told this way when I want to, you know, do things. Um, Yeah, I'll try to make it so that I'm actually facing the camera when I teach in a second. But yeah, sorry about that. I don't know what happened. I don't know why it's not working. Best I can do. So, um, today's class, we're going to start chapter 28, which is called Wave Optics. And yeah, I guess I might as well just jump in. So, actually, no, that's a lie. Before I jump in, I want to talk about the exam. So you guys just took the exam Friday. I've graded it. I have the grades up. This is the breakdown. Um, Short version is the highest score was 100. Congratulations if you are that 100. The average was a 73.5, which I'm pretty happy with. This is weird using two computers at once. It's messing with me. But yeah, the average was a 73.5, which I'm pretty happy with. To give the full breakdown, it looks like this. So it's pretty much just a ramp going up. There are three people who did have a failing grade. If you're one of them, you should look into that. Um, Other than that, with those grades in, that makes the grades in the class look like so. The average in the class is a 78.9, with the highest being a 95.24. And the letter grades in the class are then as follows. So that's the breakdown. I'm happy that no one's failing, so that's a good sign. But there you go. Since someone else just came in the room, you missed the intro. My camera's not working on my regular computer, so I'm using two computers at once, which is why the angle is kind of weird and the things might go weird because of it. Um, I assume my audio is working just fine. Seems to be. But yep, have to use two computers to do video today. That's why there's two of me in the room. Other than that, any questions about exam 2? Okay. So the one other thing I want to say before I start this chapter is remind you about final exam. Its date is Monday, December 14th from 5:30 to 7:30, although I'll allow the upload to 7:45 if you need extra time for uploading. It says last semesters will be uploaded soon. That is wrong if on two counts. First off, we didn't have this class last semester, so it'd be last year's class. And second off, it's already uploaded. So I did upload last year's exam. Take a look at it if you would like. It's a normally, well, yeah, it's going to have 9 questions. You only have to do 8 of them. Those of you who had me for physics last semester would know that was not the way I did it because we had to skip a chapter because of coronavirus. But moving forward with this, that's how it's going to be. I don't know when yet I'm going to go over last semester's exam or last year's exam. I will probably send it over when is good, work out a time people want to do it, and then just record it and post it afterwards. But that's the basic setup. Any questions there?
No.
Cool. Okay, and now I try teaching while using 3 monitors on 2 computers. This should be fun. I should be able to figure out by next class what's wrong with my camera. Normally I just have to restart my computer, but the computer that I normally use is very old and it takes it about 10 minutes to restart. So I'm just like, not doing it now. So I want to talk about the dual nature of light. I mentioned it in passing. We talked about the energy of a photon, and in passing. We haven't really got into it in detail yet. We'll do that in more detail later on. But in general, light has a dual nature. It can be treated as particles or a wave. And light acts like a particle when it needs to act like a particle. The general idea is when light acts like a particle, when light works as photons, that's why it goes that whole straight line until it hits a barrier. That's what explains the ray optics we've been covering the last 2 chapters: reflection, refraction, mirrors, and lenses. But light also can operate as a wave. And due to the fact that light is an electromagnetic wave, which is how I first introduced light, due to this fact of light, this can cause various phenomena, most commonly diffraction, interference, and polarization. And the wave-like nature of light is what can cause light to do some of its more crazy things. This chapter is mostly going to be talking about the wave nature of light and the crazy shit it can do. I'm going to get a little bit in the end of optical instruments, talk about things like telescopes and microscopes and things like that. But for the most part, we're just going to talk about the wave nature of light. Now, to understand the wave nature of light, you got to make sure you remember waves, which was chapter 10 in physics 1. So, a semester or more ago. And general idea, if you have 2 waves, they can interfere. If the maximum of a wave happens where the maximum of another wave happens, if the maximums line up, they will have constructive interference. And 2 waves can get bigger when they are in phase, when the max lines up with the max. If you have a wave, though, that the max of one wave is at the middle of another wave, it happens at the same time, that's called destructive interference, and waves can cancel each other out. I'm not going to go into this in detail. Once again, this is from Physics 1. That is just a 2-slide recap. And the second computer I'm doing is having alerts pop up. There we go. Okay. So this works when I introduced this for waves in chapter 10. General idea is this just works for waves in general. This isn't just sound waves or physical waves. This works also for light waves. And light waves, you can have constructive or destructive interference. For sustained interference, for it to continue happening, what you need is a few conditions. First is they have to be coherent. What coherent means is they must have a constant phase with respect to each other. Really, what it kind of means is the phase has to not be changing. You can't have the frequency changing as it goes. It has to be a nice constant frequency. And in order to try to get something to do constructive and destructive interference, you're going to want to have probably 2 things having nice constant phase and nothing speeding up or slowing down. Most light sources can't really do this because, like, just if I turn on a light bulb and have light shining, what's going to happen is it's just something heated. It'll be different phases. It'll be messing. The nice thing is lasers always give stuff at a very set wavelength and coherent light, a nice constant frequency and phase. Also, if you can look at this, you need identical wavelengths. It's really hard to see interference when the wavelengths are different. The reason why is because the wavelength is different. The 2 peaks might line up at one spot, but then if they'll start shifting and stop lining up as you go further down. So you really will only see this with identical wavelength light, once again, with lasers. So let's talk about how this diffraction is going to go. Let's say you take, let's just look at this picture. What this is someone taking water waves and shooting them through a barrier, through a slit, right? And as these water waves pass through the slit, what you can see is that after they go to the slit, instead of just being a nice straight line of waves going through, is they spread out and separate after they pass through. This is called diffraction. Anytime a wave goes through a slit that narrows it, it'll then go and spread out after the slit. And in fact, if I make the slit a hell of a lot smaller, you can see on this right-hand side, where's my mouse, that on this right-hand side, that it's almost like a full sphere coming out as it spreads out around. Now, in general, diffraction will occur anytime the slit is smaller than the wavelength. The longer the wavelength with respect to the opening, the larger the diffraction. And really only works when the slit width is less than the wavelength. This is why that if I like walk out the door, which you can actually see the door today, if I walk out the door, well, I have a microphone, this won't work. If you were in person, I wasn't speaking through a microphone, I walked out the door and you couldn't see me, you would still hear my voice because sound has very long wavelengths, so it's spread around the door frame. But light has very small wavelength. Like red light is 600 nanometers. We're talking about nanometer scale. And because light has such small wavelength, in order to see diffraction of light, you need a slit that's smaller than the wavelength. So you need a slit that's on the factor of 100 nanometers or less to see diffraction of light. For this reason, diffraction is not that common with light, but unless you make a very, very small slit. Now, the first person to really work this out was a man named Thomas Young. And Thomas Young created the Young's double slit experiment. This is one of the first early proofs that light has to be a wave. Because before that it was, well, they went back and forth when light was a lot. And here's the general idea. Let me switch to the video. So what I have here is some horrible focus. Really, why did I bother recording this? Okay. Actually, I'm just going to control the video instead. Where was it, the other thing about? So what I have here is a series of slits, and you can't see it, just gotta trust me, that laser is shining on things. And each of these have two small slits. Two of them, each slit is 0.04 millimeters wide, two of them 0.08 millimeters wide, and this is the distance between the slits, how far they are apart from each other. And when I shine the light through, I get this pattern. And I'm flipping from one to the other, but here, I just go to this one. Then instead of a constant light, I get bright and dark spots, a repeating pattern. And that by changing, let's go back to the beginning. By changing the size of the slit or the distance between the slits, I can change this pattern. But either way, I get a repeating pattern of bright dots. And actually, if you look at it, changing the size of the slit didn't really change anything. It was only changing the distance between the slits that I got any change. From this to that last one, looks identical. The slit size had no effect. It was the distance between the slits changing that affected. And the reason why is this interference idea. The bottom shows a kind of a GIF of these waves happening. What happens is when the waves come through each slit, they will disperse around that point. And then we'll have two series of wavefronts coming out of there. And these two series of wavefronts, the one coming up the upper and the lower slit, will interfere with each other. And what's going to happen is I'm going to get a series of bright and dark spots, normally called fringes, bright fringes and dark fringes. And the bright fringes is going to be where constructive interference happens. It's going to be where the waves coming through slit 1 and slit 2 add constructively to make a brighter spot. The dark spots will be where destructive interference happens. And it's where we get a max and a min adding up to make a 0 and cancel each other wave out. And so in this, I set up here that these bright spots are the constructive interference and the dark spots in between are the destructive interference. Now, the reason I get both these, the reason I get constructive and destructive in this setup is, well, let's just start with the center point, right? That if this light passes through slit 1 and slit 2, it's going to spread out like so. But as it spreads out, we can talk about, not talking about the whole wave, but just talking about what happens when the light hits like right here. What happens when the light hit right here? What happens when the light hit right here? And as the light goes through the various, it's going to move as a wave to that spot. If I look directly between the slits, both the light from slit 1 and the light from slit 2 travel the same distance to hit that screen at the end. And they're doing it really in the same time, probably, because it's the same light source, and they're moving at the speed of light, so it should be the same time. But the important thing is they're traveling at the same distance. they travel at the same distance, they're going to be at the same spot in the wave. That if it was all the way up on the wave, it would be all the way up on the other one. If it was down, it would be down on the other one. That they're going to be in phase and add constructively because they travel the same distance. And if I move up or down on the screen, or left or right in this case, if I move up or down on the screen, if I move a distance that I can find another bright splinge going, because I might find a thing that, yes, they travel different distances, but waves are repeating patterns. And this spot I'm looking at here, which is called Q for no apparent reason, is another bright spot. What it's going to be is that the difference in path from slit 1 and slit 2 is a multiple of distance equal to the wavelength. It's a multiple of the wavelength. That maybe this wave, if you just count the peaks, that's how I would do this. So here I have 1, 2, 3, 4, 5, 6 peaks. And here I have 1, 2, 3, 4, 5, 6, 7 peaks. And what you can find is that, yes, S1 traveled further, but S1 traveled further by exactly one wavelength. Because it traveled further by exactly one wavelength, it's still back in phase, and you get constructive. But there was going to spot between this P and Q. Well, I'm going to have that they traveled a multiple of a half a wavelength different. And what that means they travel half a wavelength different is that the light from S1 will be a max when the light from S2 is a min. And we'll get destructive interference, and they'll cancel each other out. And so these dark fringes are areas where the distance the light travels from one and the distance where light travels from 2 is equal to a half a wavelength, or a multiple of a half, either a half a wavelength, or 3 halves a wavelength, or 5 halves a wavelength, or 7 halves a wavelength. Okay? Now note, this only happens because light is a wave. If one assumes light is a particle and you just shine light through 2 slits, you should only just see like 2 lines of light because it passes through the slits and nothing else. But this light gets these bright spots and dark spots because it does this diffraction going through. And with the diffraction going through, it can spread out and interfere with each other, like on the GIF to the right. This is one of the proofs that light is a wave. And as I said, we've hinted at this before. We're going to hint at it again, but I'm just going to go into it now. That light is both a particle and a wave. And every test to prove light is a particle, it passes. Every test to prove light is a wave, it passes. Light will always do this diffraction, proving that light is a wave, even though it's also a particle. Any questions there before I get into math? So I'm going to minimize for a second because I realized I forgot to do something. Oh, no, I didn't. Okay. I thought I forgot to put my audio through my headphones because I was messing with the computers, but I didn't. Okay, so good? Okay, let's put this to math because that's always what we do. We put it to math. So let's look at light traveling through these 2 slits. And we're going to say, okay, we have the source. The source is going to put light. It's going to travel 2 slits, a slit S1, slit S2. And we're going to arbitrarily use some symbols to define things, Q being directly halfway between the points, O being straight across for the viewing screen being a distance L away, and Y the distance to some point, which we're going to call P. What I can say is that the difference in the distance the light rays travel, that the distance from S1 to P and the distance to S2 and D, the difference between those 2 distances, I'm going to use lowercase delta. And that's just going to be how off they are. Now, if I make this little yellow triangle here, I can say that delta is going to be d sine theta, where d is going to be the space between from center of slit to center of slit. And the sine theta, well, that theta is kind of weird. We'll come back to that in a second. It's just as I drew that triangle. Now, what I say is a bright fringe can happen in many spots, but a bright fringe always happens at an integer number of wavelengths. So delta is going to be lambda times a constant integer, 1, 2, 3, 4, 5, any integer. and that as long as delta is a constant times the wavelength, you will have a bright spot, where m could be 0, 1, 2, and traditionally we'll say 1, 2, 3 moving up, but also negative 1, 2, 3 going down, splitting in either direction. So 0, 1, what changed there? Oh, dark fringe, okay. Now a dark fringe will happen anytime you're a half a wavelength off. Anytime you're at, as I said before, a half, or 3 halves, or 5 halves. And so a dark spot will happen anytime you had m plus a half lambda, where m can also still be any integer. And so if delta, a bright spot will be when delta is an integer times wavelength. And because this is bothering me, one of them said 0, 1, and the other one said 1, 2, 3. It's because the 2 was just in the back. And so yeah, bright spot be m lambda, dark spot will be m plus a half lambda. Now that delta would be a real bitch to measure. So let's not work with that. Instead, let's talk about y. Well, y is how far away we are. How far in meters, or really you're going to work in millimeters, but in meters, how far away we are on the screen. But we can look at this and say, looking at this red triangle, y is L tangent theta, L being the distance to the screen. And here's where we're going to do some crazy ass shit. We're going to use something called the small angle approximation, or at least a version of the small angle approximation, which says for very small angles, the tangent of theta is about the sine of theta. And so if y is L tangent theta, well, for small angles, you know, cosine is basically 1. For small angles, tan theta, sine theta is about the same. So we're going to look at small angles. Like, this is going to be a huge spread out thing. We're going to look at a small little range normally within 2, 3 degrees. And if we do that, y instead of L tangent theta, we can say y is L sine theta. Now, if we go back to when my bright and dark spots happen, they will once again, when delta is d sine theta for, well, delta is d sine theta either way. So we can say if d sine theta equals m lambda for bright, or d sine theta equals m plus a half lambda for dark. But if I put that together with my y equals L sine theta, that means sine theta is y over L. And rearranging can tell me my bright spot will happen. My bright spot will happen anytime we have m lambda L over d. And the distance to the bright spots can be found, how far they go. You know, if I take a ruler, how far from here to here to here to here, and so on, will just be m lambda L over d. Which bright spot you want? So the 0th order, the 1st order, or really it should be 0th order, the 1st order, the 2nd order, the 3rd order, and then the 0th order, the -1, the -2, -3. So that would just be your m value times the wavelength of light, the distance to the screen, and the distance between the slits. And that's why when I did this over here and it switched the size of the slits, but not the distance between the slits, that this was one slit with a set distance, and this was a bigger slit, but the same distance between them, the pattern didn't change. The pattern only changed when I changed the distance between the slits. That this guy here, the slits will, I got to go back to focus. Slit width, 250, 500. Yep. Oh, sorry, slit width. Let's see, backwards. Yep. Yes, okay, sorry. Yeah, slit width in this, I think, is actually the space between the slits, and slit space, because that's the, no, that's the smaller. 0.04, 0.5, that's the space between them. Yep, okay. That when I changed the slit width, 0.08, 0.08, the slit width had no, changing the slit width had no effect. It was only when I changed the space between them. Now this is just the equation for bright. But I can just as easily get the Dulk equation. I can do the same derivation. I'm not going to bother doing it again. And this will tell me where every bright spot happens, where every dark spot happens. Where the first bright will happen when m equals 0, and the first dark will happen when n equals 0 on the other equation. Any questions? Okay, let's do an example problem. A screen in a Young's double slit experiment is separated from the slits by 1.2 meters. The distance between the slits is 0.03 millimeters. The second order bright fringe, so when m equals 2, is measured to be 4.5 centimeters from the center line. What is the wavelength of the light used? So we're saying L is 1.2 meters. The distance between them is 0.03 millimeters, or 0.03 times 10 to the negative 3. And we're saying for m equals 2, y is 0.045. Now, this was the second order bright fringe. Because it was a bright fringe, I'm going to use my bright equation. And say if I want to solve for the wavelength of light, well, I can multiply both sides by d, divide both sides by lm. And by plugging in my values, I can get the wavelength of light. Now, that's 5.625 times 10 to the negative 7th, but just for fun, I put that in nanometers. 562 nanometers. That is, let me think through. That's like an orangish color. No, wait, 565. No, that's red. That is red. Okay. Okay. You can also see this sometimes with reflection if you have the right setup. There was something called a Lloyd's mirror that you can cause this to happen. General idea is you have a mirror flat and a light source putting off light. And the light could either go straight to the viewing screen or could bounce off the mirror and go to the viewing screen. And it can get to point P either way, direct path or mirror path, right? If you do, ray diagrams, you could say that it's this real source. It's as if it's here at this S prime. Basically, you can treat that like an image of sorts. And what you can find if you do this with coherent light, that where P is, you actually get a dark point, assuming it's coherent light. And this is kind of weird because even if they move a fraction of the wavelength off, right? Let's say P travels a wavelength and the one going off the mirror to P is traveling like 2 wavelengths off. Even if it should be constructive, if you bounce it off a mirror like this, it suddenly becomes destructive. And this shows another step with this. Anytime, not every time, that sometimes when light bounces off a mirror, it'll have a phase shift. And the Lloyd's mirror says this would also give interference because the process of light reflecting gives it a 180-degree phase shift. What was up becomes down. What that was down becomes up on the wave. But the thing is, here we have a phase shift. Here we have suddenly light that should have been constructive becoming destructive. But it's not always a phase difference. And this is the weird thing. Anytime you hit reflect off a surface, if N1, the thing you're in, is less than N2, the thing you're reflecting off, there will be a 180-degree phase shift. This is a lot like with a traveling wave. You have a fixed end. When a wave comes down, it bounces, it comes back upside down. And so if you reflect off a surface with a larger index of refraction than you were traveling at, there will suddenly be a 180-degree phase shift. If, however, N1 is greater than N2, there will not be a phase shift. And that what was up in the wave will stay up in the wave. And so when you're reflecting off things, if you want to know what type of interference there might be, constructive or destructive, will depend on the difference between the N values. But yeah, if you like look at white light, if you look at light shining off water, there's a phase shift. And so if you'd use coherent light shading off water, you can get into destructive interference. But if instead you're underwater and you shine light out and it bounces off the air using total and tonal reflection, there won't be a phase shift at all. This can lead to another type of diffraction pattern. And interestingly, a diffraction pattern, or interference pattern, I should say, an interference pattern that doesn't need coherent light. So you're probably aware that if you like spill oil, you get like that rainbow pattern, right? Or at least there's like a thin layer of oil on something. And normally that only shows up, there's like a thin layer of oil on water. You just got to think of oil, you don't see a rainbow. But you have a thin layer of oil on water, you see this rainbow pattern. Or like a soap bubble, you'll see a little rainbow pattern. This is why. Anytime you have a very thin film of one substance on top of another substance, we can get interference patterns. If we just talk about the layer of oil on water, it is a puddle, a tiny, tiny layer of oil, and then air. It's a thin film of oil. Likewise, the soap bubble is air, a thin layer of soap, and then air again. If you have thin films, though, you can get some crazy patterns. Here's the reason why. Let's say we're going from air, we're hitting a surface A. When light hits surface, well, let me just put this whole thing up. And then nope, not that much. So what I'm going to say is I have light coming in the air, and it's going to hit a thin layer of soap. Let's say this is the soap bubble. That soap bubble on the right there. When light hits the edge of the soap bubble, some of the light will reflect, some will refract. Now this is going from air to something else. That's going to be going from a lower index of refraction to a higher index of refraction. And since we're going from a lower to a higher, there will be a 180-degree phase change. And so this light coming out one will have a phase shift. But some of the light refracts through. Some of the light goes into the soap, in the case of the bubble. When this light hits this barrier, some of the light will reflect, some will refract. And we can ignore the light that refracts, but the light that reflects there will not have a phase change. Because when light reflects, when it's going from a higher value of n to a lower value of n, there's no phase change. And so it's going from whatever the soap is to air, it's going from high to low, no phase change. What that means now is that if they traveled the same distance, my beam 1 and my beam 2 would be out of phase. But they also didn't travel the same distance. My beam 2 here went through the soap. It traveled further. Also, let's just go to refraction again in a second. We talked about this. When light refracts, its wavelength changes. And so the wavelength of the light, when it's still in this soapy water, would be different than when it was in the air. If we use this fact, and the fact that ray 2 has a longer path that's about twice the thickness, it's not exactly twice the, if it's going straight up and straight down, it'll be twice the thickness. If it's at an angle, it's going to be, a little bit more than that. But we're doing small angle approximation still, so it's about twice the thickness. You can find out where constructive and destructive interference happens. Because since there's a phase change between the light reflected off the soap and the light reflected that goes through the soap, that means I will have constructive interference for when I have the distance that travels further, twice t, is an integral plus a half value of the wavelength. And I'm saying an integral plus 1/2 value of the wavelength because of the phase change between this beam and that beam. Now, this does assume the wavelength of light in the material. But I can say the wavelength in the material is the wavelength divided by n. And this will give me that constructive interference would be 2n times the thickness, m plus a half times lambda. And destructive interference will be when They travel a set wavelength number since they were out of phase now. But I got to be careful. This equation assumes only one phase reversal. This says I'm going from a low value to a high value to a low value of n again. But what if my arrow on my bottom, what if this arrow here wasn't arrow but was something even higher value of n? Then this would all get messed up. If I instead said I went from, these are some examples, but it went from arrow to silicon oxide to silicon, which is an index refraction of 1.45 and 3.5 respectively. When I go from arrow to SiO, n went up, phase change. When I go from SiO to Si, n went up, phase change. That means I had two phase changes. And if both have a phase change, well, yeah, they both have a phase change. Now it's going to be going the opposite way. That in my equations before, the one for a bright spot is going to be now the one for a dark spot. The one for a dark spot is going to be one to a bright spot. And all those equations go out the window and have to change and shift. This gets annoying. So how we're going to deal with it is we're just going to put it in one table. This table is stolen from a textbook, but it's good. I recommend using it. It is your friend. And the general idea is identify the thin film causing interference, and look at the index of refraction before it and after it, and figure out how many phase reversals there are. If there is one phase reversal, the top equation is constructive and the bottom equation is destructive. If there's zero phase reversals or two phase reversals, the top one is destructive, the bottom one is constructive. Now, I started this with soap bubbles. So let's actually go back to that for a second before I do an example problem. The reason a soap bubble has that rainbow effect, or the thin layer of oil on water has that rainbow effect, is we're actually not doing coherent light. It's not only white light shining off it, but you have a pattern of constructive and destructive interference happening. And each wavelength will individually have this constructive and destructive interference happening, since wavelength is part of the equation. And so when you have a thin layer of oil, a thin film, or a soap bubble, the reason you see a rainbow is that for each angle you look at, some of the light, some wavelengths will have constructive interference, and some wavelengths will have destructive interference. And you'll see the pattern because all you're doing is you're looking at both sets of those, the constructive and the destructive, at the same time. Okay? Let's do a problem. Okay. A silicon monoxide thin film of thickness 90 nanometers is applied to a camera lens made of glass. This will result in a destructive interference with reflected light of what visible wavelength? So if I want to do this, I got to start by checking how many phase shifts I got. And what I'm saying is, they don't say what we're starting in. But if you're using a camera, we're probably in the air. So let's assume we're in the air. And I'm going to say I'm going from air to 1.45 to 1.55. And I say, okay, when light goes from n equals 1 to 1.45, it's going up in index of refraction. If it's going up in index of refraction, it must have a phase shift. When light goes from 1.45 to 1.55, it's going up in index of refraction. If it's going up in index of refraction, must have a phase shift. So this is two phase shifts. And if I go back to my table, two phase shifts, these are the equations. I want to say destructive interference. So destructive is this equation right here. And so destructive interference will happen when 2nt equals m plus a half times lambda. So let's take that equation. Now, I ask what visible wavelength, but m can be all sorts of stuff. So let's just say m equals 0. Well, I'm not going to plug in m for anything yet. I'm just going to rearrange. If I want to solve for lambda, I'll just divide both sides by m and a half. If m equals 0, I get that. That's in the visible range. And so that's the answer. If I did m equals 1, I would have gotten something outside the visible range. And so I get 522 nanometers. That is where there is destructive interference. That means that wavelength, the camera won't pick it up. It'll reflect off the audio. And this is actually used in cameras, thin films of stuff, in order to reflect some light out if you don't want. Certain filters work this way. Once again, this is how the soap bubble or the oil on water works also. It's just different colors interfering differently. Any questions though? This is also how Blu-ray discs work, or CDs or DVDs if you want to go old school. Oops. These pictures going across the bottom is a CD, a DVD, and a Blu-ray, respectively. What they are is they're a thin layer of metal with a protective coating. And the metal has pits in it, has little holes, tiny holes. 1.6 microns minimum pit length. There you go. 0.8 micrometers for a CD, 0.4 for a DVD, and 0.15 for the Blu-ray. What happens is as the disc spins, the laser reflects off the sequence of bumps in lower areas and just looks at the light that bounces. And the pit depth is that it's 1/4 of the wavelength of the light. And if it's 1/4 of the wavelength of the light, when it comes back, it's going in and out, it's traveled half the wavelength of the light. And so it just looks at the light that shines, and every time the light hits a pit, it gets destructive interference. You don't see any light come back. And so it can do like the binary ones and zeros because it's like there's light. Or actually, let's do it like this. So when I go across, it's just like no light, no light, light, no light, 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 no light, light, no light, and so on. That's how they work. It would be you're not just shining the light through. That would have to be clear to do that. But it's just seeing when there's light and when there isn't by when there's constructive interference or when there's destructive interference. Fun fact, the reason Blu-rays can hold so much more is literally because it's blue light. Blue light has a smaller wavelength. Because it has a smaller wavelength, you can detect smaller dots. And so Blu-ray can hold more data because it's just smaller holes. It's just making a blue laser. So this interference pattern we're talking about, it worked for the double slits. It also worked for the thin film. It also worked for these holes on a DVD. But if we get this diffraction anytime there's interference, what happens when we use a single slit? And here's the crazy thing. Double slit is pretty, kind of makes sense. That if you have a double slit, you have this pattern here, the light can spread out. If you instead shine light through a single slit, and this right here is a single slit of various widths, I also, of 0.2, or 0.02, 0.04, 0.08, and 0.16 millimeters, I also get this repeating pattern. That the single slit also shows bright spots and dark spots. And this seems kind of weird because when light's going through the double slit, you can see what they're interacting with. It's the light from one slit, light from the other interacting. But through the single slit, it should just be like spreading out. Really shouldn't be interacting with itself. But yeah, it happens. Any shape slit will cause something. And you'll see this in the lab if you watch the video. Now for a single slit pattern, it'll be a broad, intense central band flanked by secondary, less intense lights. The primary maxima and the secondary maxima. You also get the dark spots called the minima. And this can be seen with general geometry. This figure is the diffraction pattern from the shadow of a penny. What they did is they just took a laser and had it wide and shined it on a penny. And what they got is that there was rings outside, but right at the middle, right where the center of the penny blocking, there was a bright spot. And that doesn't make sense. You think you put something in front of the light should go around it. It's a shadow. But right in the center of the shadow, a bright spot happened when they used coherent light. And this is still the interference idea because light's a wave. Here's how it works. Here's my single slit, right? And as light comes from this single slit, it spreads out. But that slit has some amount of width. It has a width, we're going to call it A. When light passes through the single slit, we can look at lights from different parts of the single slit. You see, if I say each of these little arrows are photons coming through, if I look at a point, I can say light coming from the very top of the slit and light coming from the very bottom of the slit traveled a different distance. And right at the middle, so if I go right across in the middle of the slit, right across, the light from the top of the slit, light bottom of the slit will travel the same distance. But if I go up at some height, I can find spots where waves coming through the top of the slit and waves coming through the bottom of the slit traveled a different enough distance to start interfering. That if they travel a integer times 1/2 off from of a wavelength, they can interfere. And what I can do is I can talk about how they interfere at each point going up or down. In this case, this drawing, so this is saying we have a slit of width A, the light passing through going up at some angle. And I just defined 5 beams of light. The one from the very bottom from the one to the very top, they are off. They have a different in length from the middle at least. Yeah, different in length of from the middle of A over 2 sine theta. And so the difference between 1 and 3, A over 2 sine theta. The difference between 3 and 5, A over 2 sine theta. And what we can say is that if A over 2 sine theta is a half wavelength, they destructively interfere. Rearranging, that means that's when sine theta is lambda over A. And if we split the screen into 4 parts, we can find the dark spots too, as when they're like this. If we go into 6 parts, we could find the dark spots. And the dark spots would be like this. And we're like, oh, take a look. It's just going up by 1, 2, 3, and so on. Fuck it, let's just use an M again. And we can find the destructive interference from any single slit. We'll go as sine of theta, M lambda over A. Well, M is once again any integer. Now, difference here. For a double slit, M can be 0. And the first order minima for a double slit is M equals 0. But for a single slit, M cannot be 0. And the first order minima for a single slit is M equals 1. It sucks. That just is what it is, though. And this will tell you where the dark spots happen. Now, it doesn't necessarily tell you where the bright spots happen, but if you want to find a bright spot, just go halfway between dark spots. If you want to know the width of a bright spot, take 2 dark spots and subtract them. You can also find the location, because don't forget from earlier, we can say that the tangent of theta is y over L, same as before. And so I can use this and figure out exactly what value of y they're at. I'm not going to bother with the sine tangent relationship. For some reason, people never do that to this one. It's mostly because it can spread out to a wider angle. So it's not always safe to do that approximation. But we can find the height also y. Okay? Okay. It is 3:50, so I'm going to stop here. We will pick this up on Wednesday, where I'm going to make it all more complicated, because that's what I do. I make shit complicated. But other than that, have a good day, and I'll talk to you all later.